Okay, this is a video accompanying the Introduction to Rational Functions, section 4.5. And rational functions we're going to define as something that can be written as a polynomial over a polynomial. And in order to be a rational function, the polynomial in the denominator has to be at least degree 1. So, I mean, a polynomial can be the constant function, something like y equals 5, but when we talk about a rational function, you need to have a variable in the denominator for it to be called a rational function. If you just have a number in the denominator, then that's just a polynomial, because you could divide that number into each of the terms in the numerator and write it as a polynomial. Okay, so and I'll do more with that in class, but here's a very simple rational function in number 1. It is the reciprocal function, 1 over x. So going back, thinking about our domain, the domain of this would be, the only issue we have is you have a variable in the denominator, so you can't have a denominator equals 0. So you would just say the domain is everything but 0, and that's what it looks like in interval notation. Okay, so then let's think about what happens at the extremes. So as x goes towards infinity, so as x gets huge, you'd have 1 over huge value, which would make the y values go towards 0. And the same would be when we think about going towards negative infinity, 1 over negative huge, still going towards 0, whereas this would go towards 0 in the positive. When I divide by negative infinity, I'm going towards 0 from the negative side, because 1 over negative infinity will get really close to 0 on the negative side. Okay, so let's think of what happens to the value of y as x goes towards 0 from the right. Okay, so when we think as x goes towards 0 from the positive direction, I'm going to get a positive value, and it's going to explode in a positive way. What happens to the value of y as x goes to 0 from the left? So if I think about 1 over super tiny negatives, that's going to make y go towards negative infinity. Okay, so the range here, if I think about the range, in doing my analysis, I think about, okay, the denominator will be everything but 0. That's the range of x. You can put in anything except for the fact that it's in the denominator, so you can't put in 0. And that would make the range of this whole reciprocal function everything but 0. Even, odd, or neither. Okay, this is coming back. Remember, the test is always plug in negative x. And when I plug in negative x, I get 1 over negative x, which is the same thing as negative 1 over x, which is equal to negative the function. So therefore, it's odd. So remember, odd is that origin symmetry. So if we were to sketch a graph, so maybe take a moment, pause this and take a moment to sketch what this would look like. You can plot specific points. You can use the information from above. Okay, and your graph should look something like this. That's the reciprocal function. And notice as x from the right gets closer and closer to 0 from the right, the y values are exploding towards infinity, whereas when you go towards 0 from the left, it's going towards negative infinity. And in fact, we're going to say here, we're going to define some things. We're going to say that here at x equals 0, it's a vertical asymptote. I'm going to always say VA for vertical asymptote. An asymptote is something that a graph gets closer and closer to, but doesn't necessarily cross. And then, and in fact, it's never going to cross this, it can never cross a vertical asymptote because that's where it's undefined. And then let's do, there's another asymptote that I can see that the graph's getting closer and closer to, and that's a horizontal asymptote. So it's a horizontal line at y equals 0. And when we talk about a horizontal asymptote is an example of something called an end behavior asymptote. Like it's dictating what's happening at the ends of the graph. So we're going to call this horizontal asymptote an end behavior asymptote. I'm just going to call it EBA. All right, so that again is the most basic of reciprocal functions. Most basic, of rational functions, which happens to be the reciprocal function. So let's use this knowledge of what this graph looks like. And these two, we've got this vertical asymptote at x equals 0 and this horizontal or end behavior asymptote at y equals 0. And let's draw some graphs in number 2 that are transformations of this graph. So maybe try that first and pause this, and then I'll go through them. Okay, so so the directions say each, as I said, is a transformation of the reciprocal function that we talked about in 1. And feel free to plug in some points as well and sketch these graphs. So how does this graph in A of x compare to what we just did? Well, it should be shifted to the right 3. So if I draw this graph, so if it's shifted right 3, so I'm going to say shift right 3, then instead of having a vertical asymptote at x equals 0, I'm going to have one at x equals 3. It hasn't been shifted up or down, so the horizontal asymptote is still going to be the exact same. And we're going to take on the same shape here. If you want, you can find the y-intercept. The y-intercept, remember, is when you plug in 0 for x. So it's going to be negative 1/3. What about an x-intercept here? An x-intercept is what is x when y is 0? Well, there's no way 1 over x minus 3 can be 0. So as you can see from the graph, there are no x-intercepts, which makes sense algebraically as well. Okay, so that was just shifted right 3. Number b of x here. Well, instead of how does 25 over x relate to 1 over x? Well, it's just really vertically stretched. So and that's kind of hard to see, but if we want, we could plot some points. Like if we put in, for example, if I put in 5, the output's 5. Same if I put in -5, the output's -5. But overall, it's going to have the same look. It's not shifted up or down or left or right, so the asymptotes are going to be exactly the same. And yeah, it's going to be, vertically stretched, but again, it's kind of hard to see that unless you plot some other 1 over x and 25 over x on the same axes. Okay, 1 over x, remember that was in number 1, but 1 over x plus 4 just means shift up 4. Okay, so if I think about relating this to 1 over x, and if I shift up 4, that's not going to affect my vertical asymptote. We'll still be at x equals 0, but the horizontal asymptote, instead of being at y equals 0, it's going to be at y equals 4. And so this graph will look like this. And again, you could plot, there's no y-intercept because you can't, when you plug in 0 for x, you can't do 1 over x. But there would be an x-intercept here, and if you want to plot that, that's you totally can do so, or any other point you can plot just to get a feel for what's happening. But I'm strictly just sketching it using transformations. Okay, d of x, 2 things happening here. We are getting shift left 2, and not up, whoops, down 3. Down 3. Okay, so that means both asymptotes are going to change here. So down 3 now means I'm going to have a horizontal asymptote at y equals -3. And then I'm going to shift left 2 means my vertical asymptote is now at x equals -2. And again, if you want to plot some specific x and y intercepts, you're welcome to do so. The graph overall is looking something like that, just the rough sketch. Okay, so, well, what if the graph's not written in this nice transformation form? What can I do? And most of the time they're not. So but sometimes we can put it in this form. Most of the time we can, but sometimes we can. So let's talk about the sometimes we can. And I try to, in number 3, walk you through how to do so. So, so you have this function, x plus 1 over x minus 3, a polynomial over a polynomial, which is a rational function. Let's see if we can rewrite it like a transformation of 1 over x. And I started you off here by rewriting this as x minus 3 over x minus 3. So basically, I'm splitting this up so I can get a constant plus some rational function. So x minus 3 over x minus 3 is just 1. So if I'm doing, you agree that this right here, if I put it over the same denominator, so put it over that common denominator, isn't that exactly equal to the original? It is. It's equal to x plus 1 over x minus 3. But if I'm looking at how I rewrote it here, the reason I rewrote it like this is now I can say that f of x, another way to write f of x, is 1 plus 4 over x minus 3. Why is this helpful? Well, if I think of it as a transformation of 1 over x, it is shift right 3, up 1, and a vertical stretch. Again, that's going to be hard to see. 4, factor of 4. Okay, so let's see how that affects the shape of my graph. Again, we're just doing rough sketches right now. We're not really plotting specific intercepts. Okay, right 3 means that's my vertical asymptote. Up 1, that's my horizontal asymptote or end behavior asymptote. And then I'm going to sketch my graph. Using the asymptotes as a guide. Again, feel free to plot specific points. Okay, let's see if you could do one of these on your own. Maybe pause it and try to do just what I did in number 3 for number 4. And then we'll do kind of the last one, which will gear us up for kind of next class. Okay, so if you had a chance to try it, hopefully you saw that you can rewrite this as x minus 4 over x minus 4 plus 6 over x minus 4. And to double check, put it back over the common denominator of x minus 4 and see if you get x plus 2, which we would here. So this is the same as 1 plus 6 over x minus 4, which means I'm shifting my graph to the right 4. So that will be my vertical asymptote. And I'm shifting up 1. Excuse me. So that's my horizontal asymptote. Yes, it's vertically stretched by 6, which certainly is going to affect things in terms of like steepness and specific points, but the overall shape is going to be something like this. Okay. All right, so now on to the last problem. All right, right, so this one is a little bit different, and I'm guiding you through some things we're going to do on the regular when we do all types of rational functions. The first thing is finding the x-intercept. So in order for this to be equal to 0, that means the numerator has to be 0. So when you find an x-intercept of the rational function, you're always setting the numerator equal to 0. And when I do that, I get negative 5/2. So my x-intercept is negative 5/2, 0. Okay, I think some of it might have gotten cut off here, but again, this last one was trying to develop an intuition for things, and so do what you can with this last number 5, and you can look at my solutions here, and then next class we're going to pull this all together.